Okay, here we go. Hey, good morning, everybody. This is Sean Downs, Sean for Science, here with the Pasayten Institute, and today is another great morning to discuss mathematics. It's another beautiful morning here in the Manha Valley. The sun is shining. I get to sit without snow on the ground. I'm super excited about it. Today, we're going to be talking about another subgroup of SL2C, but a different kind of subgroup of SL2C, one of my favorite subgroups of SL2C, although which ones really aren't, right? The subgroup SL2Z, or Z for our British colleagues. SL2Z is a subgroup of SL2C that has integer elements for their matrix entries as opposed to complex numbers. The action of this group is kind of curious because we don't really have rational numbers anymore to talk about inverses, so it's a different kind of beast altogether, but it has fascinating applications from everything from string theory to number theory, so it's definitely worth discussing. Since today is something of a getting to know you discussion for SL2Z, we're going to just stick to the basics. We're going to describe some basic facts about the group and the group action on the Riemann sphere, and we'll introduce some curious beasts known as modular forms. But first things first, what is the deal with SL2Z? First, a proposition for you. SL2Z is generated as a group by two matrices, M1 and M2. Now, we're going to prove that maybe at a later date. It's a long and involved algorithm to go and show that it's true. But I'm going to go ahead and work through some examples to hopefully convince you that this is true. And even if you have spent a lot of time with the physicists' sigma matrices, it's worth going through these examples yourself, just kind of over and over and over again to get an experience of the flavor of how SL2Z works. Okay, so first example one. Let's consider powers of M2. When we discussed the quaternions represented in terms of the physicists' sigma matrices, we observed that the complex numbers can be represented by the matrices 1 and I times sigma 2. Well, here, M2, you may have noticed, is the same thing as I times sigma 2. And so M2 effectively has the same algebra as the unit imaginary number, that is to say the square root of -1. So, in particular, we have that M2 squared is equal to minus the identity matrix, and M2 to the fourth is given by the identity matrix, right? So what that tells us is that the inverse to M2 as a matrix is M2 cubed. Fascinating. All right, okay, so now let's move on to powers of M1, the other generator of SL2Z. So M1 is an upper triangular matrix, and if you've done anything from kind of like business calculus to linear algebra for mathematicians, probably not so much physicists, but anyway, upper triangular matrices are fun because kind of everything stays above the diagonal, and this is definitely true for this case, right? So let's consider M1 squared. You can multiply it out if you like, and what you find is you get the matrix 1, 2, 1, right? Fascinating. Well, you probably guessed from there on in, by induction, you can show that M1 to the nth power is just 1 n 0, 1. Cool. Okay, so that's something. Now, to access negative n, you might ask, how do you go about doing that? Because, the inverse of m to the 1 or the inverse of M1 to the nth power, if they're going to be group generators, they got to be in there somewhere. Where are they? It requires a little bit more effort. So this will be our third example. Let's look for the inverse of the matrix M1. So minus signs are generated, obviously, by M2, since it behaves like the square root of -1. But they also have a tendency to kind of rotate things around in the matrix space. So you might find it instructive to explicitly show or try to verify that the inverse of M1 is given by, and let's see if I get this right, M2 times M1 times M2 times M1 times M2, which is just the matrix 1, -1, 0, and 1. Cool, right? Okay. Like I said, the full proof that M1 and M2 generate SL2Z will be discussed at a later time. Okay, so let's move on to SL2Z group actions. SL2Z can be thought of as the group of automorphisms of the Riemann sphere. And the Riemann sphere, you might recall, is kind of like the complex plane with a one-point compactification, meaning that we assign infinity, complex infinity, to a point, drop a point in, and kind of wrap it together to form, at least topologically, a sphere. From this perspective, SL2Z acts on a generic element, say tau, in the Riemann sphere by this mess here, this so-called fractional linear transformation, or a Mobius transformation. And if you're anything like me, you take one look at this thing, you're like, what the hell is this? It looks like something like a kid drew, right? But rest assured, it has astonishing properties. It's a serious thing. Maybe it's a little counterintuitive to start, but hopefully I will convince you by the end of this episode that that's an amazing property. To prime you for being amazed, I want to keep the following in mind. We're talking about SL2Z, right? So that is to say matrices with determinant 1. So in particular, for some generic matrix ABCD, the determinant of that matrix must equal to 1, which means that we're looking for things like AD minus BC, and that's equal to 1. Right? Okay, so good. Now let's consider some examples of the group action. So obviously M1 is a great place to start. Looking at M1 from this perspective, we see that this maps tau to tau plus 1. To tau plus 2, to tau plus 3, all the way out to tau plus n, and back. So we see this kind of lattice structure already forming in SL2C. Interesting. And M2 acts as tau, setting tau to minus 1 over itself, which is kind of like an inversion. For a general matrix where C is not equal to 0, we see that it maps the tau at value of minus d over C to infinity, right? AKA to the North Pole. And if C vanishes, then such a matrix is going to leave the North Pole itself invariant. Okay, hopefully there's a few examples to give you some flavor of how SL2Z group actions work. Now let's consider a mapping of the Riemann sphere via the exponential function. So consider, say, the function q, which sends tau to e to the 2 pi I tau. So now let's see how the group action of SL2Z pushes forward through that map. So you obviously already saw that M1 acting on tau gives us tau plus 1, tau plus 2, tau plus 3. So this kind of lattice structure is very interesting from the perspective of this particular case, right? Because that sends 2 pi I to n to the 2 pi I n plus 1, plus 2, plus 3, and so on. So we get this periodicity kind of built in manifestly now with the exponential. Interesting. So you might begin to see how Q and SL2Z are kind of related in some respect. Now, if we restrict ourselves to the study of a certain subset of the Riemann sphere, specifically those values in the complex plane where the imaginary part of the complex plane is strictly greater than 0, the so-called upper half plane, we see that Q maps the upper half plane into the interior of the unit disk. That is to say that the unit disk itself, the unit circle under this map is actually the real numbers, right? Q, e to the 2 pi I theta, where theta is some real number, say. So it maps the real part of the complex plane to that circle, and everything that was above it gets crushed into the interior. It's kind of like the opposite of a stereographic projection that you might see either coming from the south or coming down from the north. It's similar in flavor to that sort of thing. So these facts about Q, particularly how they relate to the specific case of the upper half plane, are going to play a lot into the discussions that follow. So before moving on, it's instructive to verify some of the following claims. So one, let's verify that the upper half plane is indeed closed under the action of SL2Z. So let gamma be some matrix in SL2Z, and let tau be in the upper half plane, right? So now let's just compute gamma on tau gives us some junk, and we take the denominator to be real by multiplying by complex conjugates, as per usual we do in this particular case, and we find that the imaginary part of this mess that we've just created is nothing more than A times D minus B times C, divided by some, some real number times the imaginary part of tau, meaning that the imaginary part of gamma tau is nothing more than a real number times the imaginary part of tau itself, which thus preserves the upper half plane, which thus means that the upper half plane is closed under the action of gamma. So I'm going to leave you with one last thing to chew on for today, and we'll pick up with the implications of it next time. So consider the derivative of the map gamma of tau with respect to tau, right? So let's look. Gamma of tau is what? So we can compute, and using the quotient rule, we get a bunch of stuff, and we can combine again, and lo and behold, look what shows up. Again, our friend AD minus BC. So we see, perhaps unsurprisingly, that gamma prime of tau is nothing more than 1 over the quantity c tau plus d squared. So this pattern is going to repeat itself over and over again, and we'll become intimately familiar with it in our future discussions. But one curious fact about it is it appears to lead to an obstruction to computing SL2Z invariant contour integrals in the upper half plane. And, for anyone who's studied any kind of Riemannian geometry, you can attest that great pains are taken to ensure that the volume element of an integral is invariant under diffeomorphisms, is invariant under whatever symmetry group that you're interested in, be it SON or SUN or whatever. And, this, of course, extends naturally to discussions of Stokes' theorem, right? So if you're a physicist, maybe you discuss talking about line integrals or volume integrals, surface integrals, that kind of thing. We always want to make sure that the measure of that integration is invariant under whatever symmetries we're interested in. And so in the particular case now, we see that, well, the integration measure is clearly not invariant under SL2Z. So it would be invariant, however, if we could find a class of holomorphic functions, or meromorphic functions at the very least, that behaved kind of in a conjugate way. Namely, that under the action of some gamma in SL2Z, if f of gamma of tau were given by c tau plus d to the second power times f. So assuming these things exist, there's only a subclass of functions that lead to SL2Z invariant contour integrals in the upper half plane. And of course, we can generalize this out to arbitrary powers of k, which leads us down to the path of discussing something very interesting, that is to say, modular forms. But before we get there, these beasts are complicated discussion in and of themselves, so we're going to save that for another time. Thank you so much for watching today. I hope at least this stoked a little bit of interest in this particular subgroup of SL2C. I hope you have a great day. I hope you're getting outside. See you soon.